We start in mechanics. We're going to go through some kind of key ideas here in this session, same sort of format. And then what we'll do is, some practice questions. Please do, again, keep in touch with us if there's any problems, any questions you've got. And then short break, and then the statistics. So hopefully we're all raring to go with the mechanics. We're going to be looking at vectors, kinematics, and forces. So let's make a start. Okay, so the content we're going to cover in this part of the session is vector notation and resolving vectors. It's a really important aspect of mechanics that will filter into different things. We're going to look at kinematics, which is all to do with movement, as opposed to statics, which is stationary objects. So kinematic graphs, constant acceleration, and also a bit of projectiles as well. And then we're going to look at forces, force diagrams, and the idea of dynamics and equilibrium. So let's have a little look. So to start with, the vectors content. Now, vectors, again, all the exam boards will involve vectors. This will come up on pure, but it's really important in the mechanics that we use the correct notation and we understand what vectors are and how they work. So it's a bit of an overlap as well with kind of ideas in physics. So just kind of some key things about vectors we should consider. So in terms of a vector being almost like a movable line segment, it's a motion. It's not a coordinate. It's a sort of way of getting from A to B. So this vector here can be split into what we would call components. So I would think of the sort of change of Y. That's like the Y component. And the change of X, the sort of X component. You can break vectors at any angle down into those two separate parts, those two separate components. So a key thing to know is that the vector, sometimes written like that, but vector is basically how much it's moved left, right, how much it's moved up or down. You don't put a line, it's not a fraction, but that's how you'd express it as a column vector, which may be familiar to a lot of people, even from GCSE. The other way is to write it in the IJ notation, which is going to be really important for this part of the course. So kind of IJ notation is I being the kind of unit vector for the X direction and J being the unit vector for the Y direction. And also the magnitude, we use the modulus symbols. This is dealing with the kind of length of the vector, the size of the vector, the magnitude. And this is effectively just the Pythagoras. To get the length of that, we're going to do the Pythagoras to the components. So basically like the x squared plus y squared square rooted. How much left or right, how much up or down, and then you basically just apply Pythagoras. And that will appear a lot in mechanics. I mean, it's looking for the signifiers in the question that tell us we need to do that. Now, the other thing in year 12, that a lot of people forget they have to do, and they forget this in year 13 as well, is this idea of a unit vector. And remember, in maths, anything that says unit means of size 1. So a unit vector is parallel to the vector we have, but it has a magnitude of 1. So basically, the unit vector, which we put a hat on, is equal to the vector itself divided by the magnitude. Hopefully, we've seen this before. Okay, so it's basically the vector shrunk down so that it's still going in the same direction, but it has a length of 1. So that's what a unit vector is. It's a vector parallel to the vector we're dealing with of length 1. Right, let's keep going and let's look at these in an applied setting. So I know for some people, vectors are actually straightforward. You're really confident from pure, but we need to see this in mechanics as well. And it's another one of those big overlap topics. So combinations of any two non-parallel vectors basically can define a point on a 2D plane. And the addition of two vectors is called resultant vector. Now, in mechanics, it might also represent a force. And so that could represent the resultant force. But basically, if we add them up, if we add the components up and look at the net effect, we would then call this the resultant vector, the net effect. This is the resultant. Okay, the result of following those two vectors. So, for example, what we would have here for this one is across, it's gone A plus C, and then vertically, it's gone B plus D. Okay, and if you were to do it in the IJ notation, we would write that as like A plus C I plus B plus D J. Okay, so it's just kind of knowing that. Other little facts, if you had the negative of the V vector, then you would just change the components round. So C plus D would become minus C minus D. Okay, and likewise, if you scaled it, you would get like 2C plus 2D. Okay, so hopefully that's all clear. Right, now we're going to look at this exam question. I think we'll just whiz through this together to start with, and then we'll get further into the mechanics content. So consider the vectors. V1 is 2, 4, and V2 is minus 6A. And then we have minus 4, 4 plus A, and it says determine the possible values of A. So part A, determine the possible values of A, and state the magnitude of the vector V3 such that that is the case. Okay, so because there's more than one value, because it says determine the possible values of A, we can expect a quadratic, which might not be obvious at the start, but we need to look out for that. State means no working required, so this is probably just like a little 1 mark bit that's worth recognizing. And so let's break this down. It's maybe part I is the more involved bit. Right, so there's the two vectors we're given. And we're also told in the second part of the question that that vector plus something else equals 0. It would have a 0 resultant. So effectively, there's a link between the third thing and the sum of the other two. So let's have a little look then. So to start with, to calculate the resultant vector, that might be quite handy, because I think that was the we want to find the show that it has a magnitude of 5. So the resultant would be the two added up. So if we add the two vectors up, the resultant vector in terms of A would be 2 minus 6, which is minus 4, and then 4 plus A. And we know that the magnitude of that is 5. Now remember that the magnitude came from doing Pythagoras. So what we're going to do here is if we Pythagoras that, what we can set up is that minus 4 all squared plus 4 plus A squared must equal to 5 square root of square root of 25, so 5. And so we can tidy that up, and we are going to obtain a quadratic in A. So this is where that quadratic is emerging from. And getting all that information in, the resultant vector, and setting it up, we're getting a mark. Now, what we can do is, since we know the magnitude is 5, to sort of undo the square root sign, we can square both sides, and we therefore know that that quadratic equals 25. So we can bring it all to one side, and then therefore we can solve the quadratic for A. So let's have a little look. Very similar skills to earlier. Bring it all to one side, create a quadratic. There aren't going to be big marks for solving a quadratic because your calculators can do it. But let's have a little look. So if we do that, it does factorize nicely, and A could be equal to -1 or -7. Okay. So let's have a little look. So now for the third part, considering the diagram, we know the resultant, and we're also told that the sum of these three vectors is 0. So effectively, V3 must be the negative of the resultant that we just worked out. So it's actually not as bad as it maybe first looks. So since we know that V3 has a length of 5, then what we can do, and we were actually just asked for the length. So since it's just the reverse of it, if I go back to the question, the magnitude of it must also be 5. The magnitude of these two bits was 5. So that's why it was a 1 mark. State that question. There we go. And that was the mark that we could have done for 1 mark. So it wouldn't require any working or any further working. Right, so let's look at this situation here now. Resolving vectors. So what we've got is we can resolve a vector by taking its components in perpendicular directions. So X and Y directions. So for example, if we know that this is theta, then across is kind of like the I component, and up is like the J component, or the I and J are the unit vectors in those directions. And we can look at what scalar of each of those we have. Then what we can think of, if we think of any individual point on there, so let's say that vector, we're resolving it, we need to almost think about Pythagoras and trigonometry. So if I care about how far across it is in an X sense and how far up in Y, I want to find those values, then think about it like this. X is equal to the magnitude of R, the size of R, times by, because it's the adjacent, cos theta, and that will give me the X component. And then in a similar way, Y would be equal to the magnitude of R times sine of theta. Okay. So what we can do is if we then wanted to write the vector in the IJ form, we could say that V is equal to nearly J. Okay. Right, excellent. So if I then wanted, say, for example, to find theta, you know that tan theta is opposite over adjacent, which would be like R sine theta over R cos theta, which equals Y over X, that over that, which is what we'd expect, opposite over adjacent. Right, so let's look at an exam style question with this, and then we're going to push on to some other things. So for this one here, I'm going to give you a few minutes to have a little look at it, and then we're going to move on to kinematics. So we've got a 3 mark question. Consider the vector V with magnitude 4, 3, and it makes an angle of 30 degrees to the x-axis. Write V in the form AI plus B lots of the vector J, and let W equal V plus 1, 1. Using your previous result, calculate the angle W makes with a horizontal. Give your answer to 3 sig figs. I'm going to give you a 1.5 minute head start, and then what we'll do is we'll work through this together. So use the diagram, give it a quick go, and then we'll whiz through and we'll be on to kinematics. Brilliant. So I know a lot of you've done vectors in Pure before, which is great. Let's give this a try and see how we go. Okay, here we go. So let's have a little look. So we're considering the vector with that magnitude and that angle with the axes. So there we are. That's the vector drawn out. Let's have a little look. So the diagram clearly shows most of the required information as a reference to the question. So we want to calculate the components using the magnitude and the angle. Right, so let's do that. So we can find the x component and the y component using SOHCAHTOA, using basic trigonometry, and then we know the kind of I and j parts. So we know the modulus is 4√3, and we know the angle is 30, and we can try and keep it nice and exact. So if we do that for each of those, 4√3 times cos 30, 4√3 times sine 30, that's what we get. And even in mechanics, we still try our best to sort of keep things exact. And then we put it back in the IJ form that they asked for. So that was just SOHCAHTOA. That was just kind of your trigonometry to start with. Let's keep going. So then we're going to calculate this new vector W, and let's think about what information we have. So this vector is the vector we had plus 1, 1. So if we combine that information that we now know, 6 and 2√3 plus 1, 1, this is the vector we get. So we know how much across it's moved for x, how much up it's moved in the y direction. And so what we can do is we can fill that in and again create a new right angle triangle situation. So these are the components. This is what we have. And if we want to find the angle, we do inverse tan, arctan of the opposite over the adjacent. So the y over the x part. And we can do that and we can find the angle to three significant figures as 32.5 degrees. So well done if you worked ahead and you got that answer. That is brilliant. And just check you agree with that and you're happy with that. Cool. Right, let's keep going. So we're going to now move on to kinematics, which is huge. This is a topic that just grows and grows. And in year 13, it's kind of comes back with a vengeance as well. And we really want to be confident with this in year 12, because for some people, it's very new. If you've done physics, you might have seen a bit of SUVAT, but this is a really big topic. It's all to do with movement, which is a key part of mechanics. So all the boards test this in a very similar way. And there's lots of key considerations that we need to look out for. So we're going to look at this topic as much as we can here. Just looking at the start of this, displacement time graphs, we're going to look at, there's actually some really key things going on with this sort of shape. So for a displacement time graph, this actually encapsulates all the aspects of kinematics, calculus, SUVAT, and speed distance time. So what we've got here is that if we were to like look at the gradient at an individual point, so for example, if I added a tangent here, the gradient of that tangent at that point would give the instantaneous velocity. So the gradient of the tangent at the point gives the instantaneous velocity. Okay, now what I do want to point out is that this part of the graph you would deal with using calculus. This is like the variable acceleration situation. Because the gradient is getting less, this actually represents deceleration because the velocity is decreasing. So deceleration decrease because of a decreasing gradient, a decreasing velocity. So actually, it would depend if it's a displacement time graph or a velocity time graph. But for this situation, we've got to consider there's so many different ways kinematics could sort of present itself. Now here, this actually shows us if this is a displacement time graph, this is actually at rest because the displacement isn't changing. And then here, this would mean there's a negative constant velocity. Does that all make sense? So it's kind of maybe it's going backwards or something to where it started. Great. Right, let's look at the next situation here, where we have the following. So this velocity time graph plots an object's velocity against time. So here we have lots going on. But basically what we have is for a velocity time graph, the area underneath represents what? And this is where we'll see integration sort of fits into stuff. The area underneath the graph actually represents the displacement. And notice the displacement could be negative. Okay. So what we have is at this stage of motion, we have like non-uniform acceleration. So this is where you would use calculus. It's not a fixed number. Here, for this chunk of the graph, this doesn't mean it's stationary. Because it's a velocity time graph, this actually represents that the velocity is constant. So it's not accelerating, but it's moving at a fixed speed. This would actually represent here constant deceleration. And then again, constant velocity, even though it's negative, and then a kind of constant acceleration. Now, just bear in mind for this kind of graph, which is a bit weird, if you were asked for the actual total displacement, it could be zero. If this area was equal to this area, it could cancel itself out and be back to the start. So the distance is actually the two areas added up. And this does tie in with integration. So imagine I call all of this area 1 and all of this area 2. However, the displacement is the difference. If we think of them as an area. Right, good. So let's keep going with this and see how we get on. We're going to do another big exam question because it's these graph ones that do trip people up quite a lot. So let's have a little look. So here we go. So Elliot typically cycles to work. He starts his day at home and works in his office from 9 a.m. till 5. His journey is shown in the following displacement time graph, where S is in kilometers, T is in hours after 7 a.m. Determine how far Elliot's office is from home. Calculate the speed on the way home. And that's important, not the velocity, but the speed. And then he receives a new bike for Christmas, which makes him like allows him to cycle twice as fast. And we want to see basically change the graph, the displacement time graph, to show how the journey has changed. Okay, so 4 steps. We've got to kind of interpret graphs, check the details, and then we need precision and units and everything as well. So here's the graph. Again, I'm going to give you just a minute for this. Make a start if you can, if you've got that in front of you, and then we'll review this thoroughly together and keep going with this kinematics topic. The next thing we'll build in is SUVAP. So another minute, let's see how we go. Okay, so let's have a little look. So there's the graph that shows the journey. So we want to look at the displacement, looking at the start where Elliot's at work. So he's at work from 9 to 5, which is the flat line. So we basically just need to read off S from the start. So that's hopefully a really simple one, because from 9 to 5, that's when he's at work. We care about the Y value of the displacement for the whole thing. So that will be at 24. So basically 24, is that right? 24 kilometers away, 1 mark. Okay, so that was just reading off a graph. Right, calculate the gradient. So the gradient on the final part represents the return home journey. So we want the speed, and the speed is the magnitude. So even though the velocity will be a negative gradient, it's effectively just saying turn it positive. So, and we need to give the right units as well. So on the return home, if we look at the gradient there, 24 kilometers in 2 hours. So basically 12 kilometers per hour. And we wouldn't say minus, we'd say plus, because we want the speed. So we just want the magnitude of that. Okay, brilliant. Right. Now, this is the bit about the new bike. So what we want to do is we want to look at what we already have, and we want to double the speeds. So the time t equals 2, basically, we'll look at t equals 2 and t equals 10, and the gradient will be twice as steep. That's what we know, because it's quicker. So what we want to do is we want to, this is easy to mess up, but we want it to be steeper. Now, we still want him to be getting to work at 9. So this point and this point needs to be the same, and leaving at 5, but he won't need to leave as early. So we can work out the gradient, make it doubly steep, and then that means that he can leave at a later time. Good, okay. So what we're going to do now, we're going to go on to Suvat, which hopefully everyone who's done kinematics has seen and has seen these symbols. Okay, so Suvat. Now, just check your exam board. As we said earlier, do check your rubric for your exams, but also the formula booklet. And if you will be given the Suvat equations in your exam booklet. So if not, they're worth knowing anyway. S, U, V, A, and T are the different variables we use. So S equals UT plus half AT squared. That's a very common one we use. V equals U plus AT. S equals U plus V over 2 times T. V squared equals U squared plus 2AS. So it's basically knowing what they are, how to rearrange them, and looking at what we have and what we want. So I would always list out what ones we have and what ones we don't have. And by combining them in different ways, you can actually generate the other ones. So another one we do also have is S equals VT minus a half AT squared. And then what I think we have is we have 5 different equations there, all with 4 different combinations of the letters, of the 5 different letters and variables. So each equation contains 4 of the 5 variables. And if you know 3 of them, you can use the correct one to find the 4th that you want. Okay. So some questions will involve multiple parts of Suvat. Let's look at some examples and how we'd approach this. But this is when it says constant acceleration. So if the problems involve gravity, or we recognize that it says the words explicitly constant acceleration, I would straight away write out Suvat. So if it says it has constant acceleration, I would immediately write S, U, V, A, and T, and look at what I want, what I have, and what I need. So, for example, if an object begins at rest, this is a really important assumption, and people do a lot of things like this wrong. If it starts from rest, the initial velocity is 0, because U is the initial velocity, V is the final velocity. Sometimes people think when something hits the ground, its velocity is 0, but it will hit the ground with speed. So that's not quite right. Moments after, the speed would be 0. But that's a really important consideration. But what we're saying is, for this particular case, what we notice often happens is that this would then become s equals half at squared if u is 0. Okay, and in this particular case, v squared would become 2as if u is 0. For motion with gravity, it is suvat, and a is 9.8 or 9.81, depending on your exam board. So do look out for what your board states to use as gravity. And then if it's an object thrown up in the air, this is really important as well. At the highest point, the velocity is 0 because it's not moving up or down. So it's got 0 positive and 0 negative velocity. So it's actually at 0. It's instantaneously at rest. So that's a really important one to consider as well. And those that have done projectiles, those that have done objects being thrown and like motion under gravity will recognize that. So this would be brilliant to do an example of this now. And we're going to just work through this question together. So a coyote is trying to catch a fast flightless bird. The coyote runs at constant speed of 10 meters per second. When it is 80 meters from the bird runs away. It starts running from rest with constant acceleration. After 4 seconds, the bird is running at 8 meters per second. Calculate the bird's acceleration. If the bird started running when the coyote starts accelerating at 2.5 meters per second squared, calculate the time it would take the coyote to catch the bird after the latter starts running. Give your answer to 3 significant figures. Right, this feels like one of these questions that we're like, oh no, too much to take in. I've got to visualize it all. There's so much going on. It's fine. We're going to just break this down and think about what we know. So 5 marks across 2 parts. One requires more work, so it'll be split 2, 3. There's lots of values to plug into suvat that we've been given. So there's loads. There's kind of 2 situations even. So speed of 10 meters per second, 80 meters from rest. Constant acceleration tells us it is suvat. At 4 seconds, that speed. There we go. That's the acceleration. 3SF for the answer. So there's loads. There's loads to sub in. 2 moving bodies with 2 different conditions. That's another kind of key thing to look out for. So let's write down what we know. And this is a really good approach that you guys might want to make a note of, highlight, and just clarify. So if we're trying to find the bird's acceleration for the first part, we know the bird's starting speed, u, is 0. We know the top speed is 8 and the over a time period of 4, and we're looking for a. So which thing uses u, v, a, and t? It's this one. Okay, so this is what we're going to use. And by selecting the correct suvat, we're already potentially picking up a mark, because all we need to do with that is sub the values in. So let's do this together. For the first part of the question, we're looking for the acceleration, and we know that v equals u plus at. So a is the change in velocity over time. By definition, that's what acceleration is. The change in the velocity divided by time, the rate of change of speed. So 8 minus 0 over 4 seconds. It's accelerated from nothing to 8 in 4 seconds. So it's gone 2 meters per second. 2 meters per second quicker per second. Right. So so that's the first part done. 2 marks for that. Hopefully we're all good. Now, this is the bit where it gets a bit involved. So we're trying to find the time for the coyote and the bird to meet. So let's call that t. This is the variable we're exploring and we're trying to find. Now we've got 2 different things going on. And for a lot of people, that's really awful to like track and keep in check. But basically, let's list out what we have, which is quite a lot. The coyote's initial speed is 10. The bird's initial speed is 0. The acceleration of the coyote is 2.5 because they told us. The bird we've just worked out is 2. So it does look like it's going to catch it quite quickly because it's already running along and it's accelerating quicker than the bird. Okay, so let's have a little look. So if we were to determine the relationship between the two, this is really important as well. And there's a lot of practice questions like this people struggle to work through. There is a link with the displacement. They are 80 meters apart. That's the thing we could forget to use. So if we were going to define the displacement, the position is going to be 80 meters. The two locations will be 80 meters apart. So the displacement from a fixed origin of the coyote will need to be 80 plus the distance the bird travels. So what we're saying is for the coyote to catch the bird, it basically needs to make up 80 meters worth of ground as well as the distance that the bird has traveled in that time. So it's a strange concept, but the displacement to make up that ground of 80 meters, the bird's displacement plus the 80-meter head start needs to equal to the coyote's displacement. So something along the lines of this that shows that this is a key consideration is going to help us bring this all together. And this is the kind of bit of the question I completely understand people get a little bit lost in, but hopefully we can fathom that's the key thing. That's really important, and we need to write that in some way. Now, what we have is we have the initial velocity of the coyote is 10. The initial velocity of the bird is 0. The acceleration of the coyote is 2.5, and the acceleration of the bird is 2. And we're looking for the time. And we also know a link between the displacements. So S, U, A, and T is going to be our favorite classic one. It's this. We're going to do that for the bird, and we're going to do that for the coyote. So for the coyote, the displacement is the initial velocity times time plus half the acceleration times time squared. And that's the equation we form. Now, just pause there and check we're okay. We're about to do the exact same thing, but for the bird. So the bird, that's tidied up for the coyote. Now for the bird, the displacement is the initial velocity, which is 0, plus half times the acceleration times the time squared. The bird actually ends up with a displacement of t squared. That's really nice. So we can now link these together and we form a quadratic. So I'll maybe give you 30 seconds to try and put that all together, see how we go. And this is yet another example of where mechanics might have a quadratic in it, but you just use your calculator. In real life, they're not going to be nice, perfect integer values. So we can put t squared in the first equation, use a bit of substitution, see how we go. Brilliant. Bring it all to one side. Get a single quadratic in terms of t. And then let's solve that. And you could use the quadratic formula. You could actually just use your polynomial solver on your calculator. And we get a time of 6.83 seconds. And a final mark for giving the right units and the right number of decimal places as well. Okay, so that's really, really important. Now, let's keep going. That was really good. Hopefully that was clear. I think that was a brilliant question because it's one of those where there's two things going on. And in an exam, something that could take you 5 minutes could easily take you 20 minutes. And we could lose a lot of time and a lot of confidence. So it's just about stating the variables really clearly in a way that works for you and then applying the correct Suvat equations. Right, let's keep going. So we're going to now look at projectiles, which for some people you do very kind of fully in year 13, but we all often start it in year 12 where we look at kind of an object projected up that falls back. So I'm actually going to just talk about what a projectile is. If, for example, a ball is kicked at an angle, that projectile has a horizontal and vertical component. if you throw a ball into the air, that is also a projectile, but it might not have any horizontal component. The key thing that I think I don't stress enough to my classes, and it's really important, is that it's not the same as something being flown across by like having an engine or something powering it with a force behind it. It's projected. So after that, it's effectively in free fall, but it's moving. So there's no constant like driving force, like a car driving along. A projectile is like it's been fired and there's nothing driving it anymore. The only thing that's happening is it's falling to the ground because of the force of gravity. Okay, so that is what a projectile is. And gravity, the only acceleration that's happening is obviously gravity, and that's happening downwards. Okay, so it's like if you imagine something fell out of a car window, you threw something out of a car window, people think it goes back or something. It's just basically not going forward as quick. So that's why it sort of feels like that. But basically it's only accelerating to the floor. So what we'll do is we're going to look at different situations here, but a projectile can experience acceleration whilst moving horizontally as well. So these are like the harder questions that we're going to look at. So what I really want to make clear here is if this ball was like booted at this angle, so there's theta, there's the angle from the ground that it's booted. So you have an initial speed horizontally and an initial kind of vertical speed as well. And the actual magnitude or hypotenuse is the speed it's kicked with. Okay, it's projected with. So there's the actual speed, which is in the direction of motion, and it has a horizontal and a vertical component. Okay, so that's what we need to consider. Now, as this thing goes up, its upward speed is decreasing because the acceleration is trying to pull it down. So at the top, what we actually need to consider is that some people go, well, it's at rest at the top. It is vertically, instantaneously not going up or down anymore, but it is still moving horizontally. And it's only the horizontal component of the speed that's still there. And likewise, at this point here, it's still moving horizontally with the same speed, but it's now got a bit of a downwards component as well. And it ends up going that way. And so I think of this as like an evolving triangle where the horizontal speed doesn't change, but the vertical speed gets less and less and less until it's just going across. And then it starts going down and the triangle sort of becomes negative. And the way I visualize this, I think this is a really important thing to explain, is that the only acceleration is downwards. So in a vertical sense, across, it's actually moving at a constant speed because it's been projected. There's no acceleration acrossways. So the way I describe this is if you imagine someone booting a ball off a cliff into the sea, if you were completely opposite them doing that, you would see it kind of go up and down and it would be hurtling towards the sea. And it would almost be like you just threw it up and down on the spot if you had no depth perception of it coming towards you. So it'd slow down, reach a peak, and then speed up to the water because it's accelerating downwards the whole time. Now, the way I visualize this horizontally is imagine if you were in an aeroplane above that situation, you would just see it go across and then disappear when it hits the water. It wouldn't accelerate across and it wouldn't decelerate across. So if you had like a bird's eye view of this projectile off the cliff, you would see it just go across and then it would disappear when it's in the water. But it wouldn't speed up or slow down horizontally. So that's the thing I want to make clear, because that's where projectiles get quite confusing. So the vertical component of velocity is 0 at the top of the arc. However, it is still moving horizontally the whole time. So the horizontal velocity is constant. That's the key thing. So I'm hoping that's clear to everyone, but that's the bit we don't always get time to discuss enough. So please do ask if you're still unsure. Right, let's just check how we're doing. I think we're good. So we're going to keep pushing on, and then we've got statistics after this session. So we've got a bit more kinematics, and then we're going to look at dynamics and force diagrams. So let's look at projectiles a little bit further. So as we said, the vertical component is basically experiencing uniform acceleration due to gravity. So in a vertical sense, we have minus g. We think of upwards as positive. The initial is u sine theta, because if we go back to the diagram, it's the speed and it's the opposite. So it's u sine of the angle is how much upward speed it has. So it's u sine theta. The displacement is the height. The time, if we're looking at this, is basically, so if we're looking at the time of the whole thing, and then if we were looking at a particular situation where we wanted it to the top, that would be when v is 0. So the time to the top would actually be half the time of the flight. If we look at this, so if we were trying to find the height that a projectile gets to, you would use the velocity as 0 for the vertical sense. Now notice that horizontally, the acceleration is 0. The horizontal speed initially is u cos theta, but the final initial velocity would be the same because it's not accelerating. So the displacement, we actually call this the range, how far it travels horizontally. Who's seen that before? And then this would be the time of flight till it lands back to the ground. And we can use that combination of stuff to work out things like how high the projectile goes, how far the range is, the time of flight, and so on. But remember, basically, we're dealing with suvat in the vertical, speed, distance, time in the horizontal. Right, let's look at a question. So we'll do this, and then we'll actually, it's a really good one to do, and then we'll do a little bit of forces and dynamics. So this will be a nice one to look at. So, and here we go. An island is being attacked by pirates. The soldiers on the island try to shoot the pirates by firing a cannon from a cliff 100 meters above sea level at the edge of the island. The ship and the cannon are both facing each other, with the front of the ship being 0.2 kilometers away from the base of the cliff. So we're probably going to do a little drawing of this. The ship is 25 meters long. The soldiers point the cannon 5 degrees below the horizontal and fire the cannonball at 50 meters per second, as shown in the diagram we'll see. Neglecting air resistance and treating height of the ship as negligible, calculate whether the ship will be hit by the cannonball. Right, 5-step question. Lots of calculation needed, lots of numbers in there. Horizontal component is uniform. The vertical has gravity, so it's suvat. And we want to know where the ball hits the sea or the ship. And then we're going to compare it to the position of the ship. Okay, here we go. Here's our diagram. Let's have a little look. So I'll give you a minute to think about what we could add to this diagram, what we know. Because this, again, it is a projectile, but it's not projected up. It's actually projected this way. So it might go like that. It might go like that. It might go like that. We've got to work this out. So let's think about what we do know, what values we know, what we can fill in for suvat. I'll give you 1 minute, 1.5 minutes, and then I'll start filling in some bits as well. But here we go. It's an interesting scenario here. Very clear diagram. Let's give it a go. Right, let's see how we're doing. So quite a lot to take in. We've got a lot of distances, we've got a lot of values, we've got triangle situation to look at. So we need to resolve it into horizontal and vertical components. And the more involved bit is the vertical direction. So let's deal with that first. So the initial velocity vertically is 50 sine 5. And this is also an important exam point for those of you doing mocks, for those of you doing your real exams. In general, the mechanics will be in degrees. So when you have your two pure exams first, which are typically in radians, and then you do mechanics, which is in degrees, I would make sure my calculator swapped over. There's only one very particular niche part of mechanics where you might need radians, and that's for the calculus stuff for variable acceleration. Pretty much all of mechanics is in degrees. So do check your calculators in the right setting, is what I'm saying. Right. So the displacement vertically is 100. And notice that for this, I'm resolving downwards as positive. There would be no reason to put upwards as positive because it's fired downwards. Gravity's happening downwards. It ends up downwards. So everything would have minus signs. So you might as well make the downwards direction the positive direction. And then everything's positive. So your initial velocity, your displacement, and your acceleration. And the key link between the horizontal and the vertical components is the time, because it's got to happen at all in the same time if it's happening in one motion. So if we can find the time, then we've got the time to plug in for the horizontal. So if I can work out how long it's taken to fall 100 meters at this angle, then I can work out, well, how far horizontally has it gone in that time? So we can use SUVAT. I've got U, A, S, and T. So what we've got is the time obviously is the same for both things. So what we'll do is we'll plug that into S equals UT plus half AT squared, if you haven't already. So 100 equals 50 sine 5 times the time we're looking for, times a half acceleration, which is gravity, times T squared. And you generate a quadratic in T, which is annoying. It's not nice numbers, but you've got a quadratic solver. So let's solve it for the 1 mark. The time we find, the time we achieve, if you do that, again, you don't need quadratic formula. If you've got a quicker way, is 4.09 seconds or minus 4.98 seconds, which doesn't make any sense. So it has to be the positive one. Also, guys, for sense checking, be aware that in general, most of these mechanics questions, like something falling off a cliff, something being fired, something being thrown up, is always just a matter of a few seconds. If you're getting an answer of like 20 minutes, it's definitely gone wrong. It's not going to take that long. Okay. So it's very, very quick. Now, let's keep going. So the two variables we know for horizontal, there's no acceleration. We now know the time where it hits the water or the ship. And we know it's horizontal velocity, which doesn't change. So you're literally using speed, distance, time. And all the SUVAT equations would turn into speed, distance, time if A is 0. So because the acceleration horizontally is 0, you're just looking for the displacement. So speed, distance, time, displacement is the speed times however long it's going at that speed for. So if we do that, velocity times time, that's the horizontal velocity. That's the time for which it takes to fall the 100 meters. So it will go 204 meters to 3 significant figures. We now need to interpret this. Does it hit the ship? And of course, because it's between 200 and 225 meters, it will hit the ship. The ship was 200 meters away and 25 meters long. So it does hit the ship. Okay. So I think that was a really good question to go through. What we're going to do now is we're going to look at forces, talk a little bit about force diagrams, resolving as well, and even a little bit of slopes, because this does really stretch people. It's kind of, again, a topic that immediately goes through into year 13. Those of you that are in year 12 and maybe haven't done all of this yet, a lot of the time after predictor exams and mocks and stuff, a lot of schools will start this content before the summer as well, because of the mechanics content of year 13 is quite heavy. So let's have a little look. So forces and force diagrams, we very much start even early on in year 12, and it's a skill that sees us through the whole course. So let's look at this situation. So to determine the acceleration of an object, we resolve forces. So we know some key things. We know F equals ma, Newton's second law, and sometimes the forces are equal to 0, depending on what's happening. Now, if we look at what's happening to the right, similar sort of thing, lots of trigonometry. This is going to be F, sorry, not F, T cos theta. This is going to be T sine theta. So you've got sort of a resistance frictional force here, the weight down, and then this thing holding him up, which has a horizontal and a vertical component. Okay, so to the right, we have, I'm resolving, forces horizontally would be, if they're balanced, T cos theta, actually minus F. So we would either equal it to 0 or ma, mass times acceleration if accelerating. But ultimately, that's the resultant force. So that force minus that force. And then if we look at the vertical components, up and down, so the forces vertically, we would have T sine theta minus mg, the weight. Okay, the other thing we need to consider is Newton's second law will often come up, which is F equals ma. So the force could be a vector quantity, the acceleration a vector quantity, but mass is always a scalar. Okay, right, so I'm going to move this on. Now, this is another situation that I really want to make clear for people, even if you haven't done much of this yet. I've had really good questions recently on this, and it's reminded me of like the common misconceptions that people have for this part of mechanics. There is a lot going on with these diagrams. This is an object resting on a slope, and you have to add a lot of annotations to this. The biggest bit of advice I can say for questions like this, I mentioned it earlier, is I would always draw this diagram half a page at least. Make it nice and big, nice and clear. Now, parallel to the slope, I personally denote that as like this notation. So if it's parallel, perpendicular and horizontal, I would just do up and across. But because this is on a slope, we've almost got to turn our head and resolve parallel and perpendicular. So I would denote this one like this. That's personally how I denote that we're resolving parallel to the slope and perpendicular. Almost like how on the floor we do vertical and horizontal, we're just turning it and doing parallel and perpendicular so that everything's sort of neat. Now, the key thing here is we are going to need to break some things into components. So this tension that's pulling the thing up the slope is parallel, and there could be friction as well, but there isn't for this case. Now, this weight, which acts straight down to the center of the earth, has two components. Okay, actually, I'm going to use color blue here. It has a kind of into the slope effect and a down the slope effect. So what we're saying is the weight is doing two things. It's pulling it into the slope and keeping it on the slope at the same time as actually making it want to fall down the slope. So it has two components, one component holding it on the slope and one making it actually slide. So what we think of, and the key thing to remember, is this angle here by similar triangles is the same angle as the slope. Okay, and there's the first time I saw that, I struggled to work out why that was, but it's similar triangles and you can work it out easily using a few like little methods there, but we don't have time right now to do that. So I would say if you can accept that, do that, that is theta. Hopefully people have seen that before, but it's a similar triangle to the slope itself, which is really cool. But what that means is that this bit here is mg cos theta. Oops. And this bit here is mg sine theta. So when I come to resolve parallel to the slope, if this is balanced, if this is an equilibrium, then we have t equals mg sine theta. The amount that this is pulling it up is supporting the amount of weight that's pulling it down. So it's not moving. And if it's perpendicular, the normal reaction is equal to how much it's forcing it into the slope. Okay. Now, another really important point, because I know people have a real issue with these questions. This is very different to a ladders or moment question. If there's a rod leaning between a wall and the floor, there's a reaction there and there. The normal reaction happens at the point of contact between two surfaces. So on a ladder, you would never draw, if there was a man on the ladder, you'd never draw a reaction there because it's not a solid surface. This is actually the floor. So this is literally like when you have a box on the floor and there's a normal reaction, but we've just turned the floor like that. That's why there's a normal reaction. A normal reaction is when it's the point of contact of something and a surface, a solid ground or a wall, okay? Not a stick that's wedged between a wall and the floor. The reactions will happen at the floor and at the wall, not in the middle. So soon as you see a diagonal line, you don't just stick a normal reaction. That's only if that is ground, if that's the solid ground. This is an object leaning on a slope. There will be a reaction because underneath it is the floor. Hopefully that's clear. And this is how we resolve it. So we'll look at some questions with this because what we start seeing is it ties in with pulleys, suvat, like lots of stuff gets thrown in. And I would anticipate one of your big exam questions will be this, because they have to choose big questions that link year 12 and 13 content. So this is great because it has Newton's laws, frictions, pulleys, suvat. There's lots going on, force diagrams. You could almost bank on this type of question being really like important in the exam. Now, friction, there is a definition for friction, and friction is equal. Sorry, 1 second, guys. The pen's been a bit slow. Friction is equal to mu r. Now, what I'm going to do, I'm just going to pause that there for a second. I might just add this in. I'm going to let you see this question in a second. I'm just hoping the pen will come back to life. Oh, here we go. So friction, who's done friction before? Hopefully we've seen it before. Friction is equal to mu times r. So what I'm going to do is give you an exam question to do this. And also on this side of the diagram, T is equal to mg. Right, I've done something really silly. I've put the pen white. That's why we couldn't see it. So all fixed, panic over, mg and T there. So what we were saying is friction is less than or equal to mu r. So basically the maximum friction, and mu is the coefficient of friction. Has everyone seen that before? Some of you might not have seen that, but this is given to you in the question. Some of the year 12 questions, they actually just tell you what the force of friction actually is. But yeah, the tension, as I said, equals mg, as we'd expect on the other side of the pulley. So here's a quick question we'll do. And then after this, I think we're going to take a short break before starting the statistics content. So let's look at this one together. This is a really good one to do. And let's look at the key information we're given. So tile on the roof becomes loose and slides down from rest. That's important. That's suggesting something. The roof is a horizontal, modeled as a plane inclined at 30. The coefficient of friction, so mu, is 0.4. Particle of mass m, calculate the acceleration. So we're going to use a bit of SUVAT as well. So there's lots going on here, lots of information. And also we've got to resolve forces, think about F equals ma, and so on. So let's have a little look. So here's the diagram. There's the tile, there's the friction, there's the weight. Now the first thing we're going to do, if we start breaking this into components, I would make sure that diagram was clear, we understood that. And then we'd have 30 degrees in there. And then I would separate this as W cos 30 and W sine 30. And then let's have a little look. We also know mu is 0.4. So horizontal components include this and this. And the vertical components are this and this. So let's look at resolving them into the separate thing like we just did. So that's the into the slope component of the weight, and that's the parallel component of the weight. So that was just tidying those values up. So we've added those onto our diagram. Now, what we've got is resolving the forces parallel and perpendicular to the plane. So this is the one where I would personally denote it as perpendicular to the plane. And that would be the weight into the slope needs to equal R, the resultant force. So now we've got R. Now remember, that helps us find the friction, which is mu R. So 0.4 times that gives us the friction. And now we can resolve parallel to the slope. So parallel to the slope, remember, there is acceleration. So the forces aren't balanced. This is Newton's second law. This is F equals ma. The resultant force equals mass times acceleration. So the resultant force will be the weight of the tile minus the friction. And that will need to be equal to mass times acceleration. And then you can rearrange that, divide both sides by m, divide by g, and get acceleration as 1.51 meters per second squared. Cool. Right.